Hello everyone, and welcome to this video on linear equations. So in this video, I'm going to first introduce, the definition of a linear equation in n variables. Throw out some terms like coefficients and constant term and whatnot. Then I'll go over several examples where I just am going to look at an equation and determine whether or not it is a linear equation. Right, does it satisfy the definition? And then in the latter part of the video, the latter half, I'm going to talk about what the graphs of linear equations will look like in 1 dimension, 2 dimensions, 3 dimensions, and beyond that you can't really visualize, right? Because we live in 3 dimensions. It's hard to visualize the fourth dimension, fifth dimension. Okay, but the latter part will be on graphs, and I'll go over examples where I'm graphing linear equations. Right. So on this first page, just what is a linear equation in so many variables, in n variables? A linear equation in n variables. Say the variables are called, now they don't have to be called these, but say x variable 1, x1, variable, the second variable x2, third variable x3, and so on to xn, x sub n. And again, they don't have to be called x1, x2, x3. They can be called xyz or whatever, right? Just so long as I know I have n of them. So a linear equation in n variables x1 through xn has the following form. So it's a1 times x1 plus a2 times x2 plus, and so on, a3 times x3, a4 times x4, plus dot dot dot, plus an times x sub n is equal to b. Where every single one of these a1, a2, a3, a4, all the way up to a sub n are called the coefficients of these terms. So the coefficients a1, a2, up to an, those are just any real number I wish, right? So I gotta have 2x1 plus pi x2 plus the square root of 3 times x3, and so on, right? All these a numbers are any real number I want. The constant term b, right, the term without a variable attached to it, right? Every single term on the left side here has a variable, right? One of these n variables attached to it. The term that doesn't have a variable attached to it, right, will not vary, will stay the same value all the time, thus the name constant term. The constant term b is also going to be represented by some real number. Now, the expression on the left side, we're going to see this a lot in other videos you're going to see of mine. When you have a number times one thing plus a number times another thing plus, when you have all these numbers multiplied by things added together, that'll be called a linear combination of those things. And notice how all these variables are to the first power as well. But this side here, with the a1 times x1 plus a2 times x2 plus a3 and so on, this is called a linear combination. Right? A linear combination of those variables of x1, x2, x3, up to xn. Alright, so when I talk about a linear combination of some stuff, it just means you're adding up multiples of those things. Some number times x1 plus some number times x2 plus some number times x3 plus dot 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 plus some number times xn. That's all a linear combination is. And again, you're going to see this, the words linear combination come up a lot in other videos, especially if you're in a linear algebra class. So some other things to point out, again, notice again all the variables are to the first power. They have an exponent of 1. There aren't any variables in denominators or in any special symbols. Right? So it's just some things I'm noticing, some things I'll point out. So each variable, just the variables, each variable has an exponent or a power of 1. It has an exponent of 1. Right? Another way you could say that is every single term with a variable has a degree of 1, right? Just a variable to the first power in it. There are no variables in denominators, right? Because if you have a variable in a denominator, that would imply that you have a variable to a negative power. If you recall how negative exponents worked. So notice there are no variables in denominators. Right. Another thing to notice is that there are no special symbols around the variables. So there's no roots like square root, cube root of a variable. There's there's no variables in exponents. There's no absolute value around a variable. There's no logarithms around a variable. Right, so no sines or cosines. There's no special functions. I'll say no, special symbols with a variable in it. So a linear equation is basically just the most basic kind of equation you can have. Right, so no special symbols. So like I said, no, there's none of this. There's no square root of x, no cube root of x, or nth root of x. There's no like e to the x, right? An exponential function. There's no special functions. Natural log of x, cosine of x, tangent of x, etc. Right, and absolute value of x. There's none of that. Right? Nothing. No special symbols with a variable in it. Right. Right, so again, the most basic kind of equation that you can possibly write. All right, and when I say that it has this form, it doesn't mean that it has to start this way. As long as I can do some manipulation, adding and subtracting terms to both sides and get an equation to look like this, then we would still consider it to be a linear equation in so many variables. Alright, so now that I've got the definition down, let's take a look at some examples. And just simply, I'm asked to determine whether the equation is linear or not. So, first example, again, for my first several examples in this video, it's simply determine whether the equation is a linear equation. So I've got 5 times variable x1 plus variable x2 minus 7 times variable x3 equals 4. All right, this looks exactly like I had on the previous page, right? Some number times a variable to the first power plus some number, say a2, times another variable to the first power plus another number, say a3, times a variable x3 to the first power equals, and then some constant term, right? Some term without a variable. It looks exactly like this. And notice there are no, every variable, as I mentioned, every variable, x1, x2, and x3 has an exponent of 1. every term has a degree of 1. Right? Every term has a degree of 1, meaning only a single variable to the first power in it. No special symbols with variables in it, right? There's no square root of x1 or absolute value of x2 or log of x3 or anything like that. It's just simply a linear combination of the variables to the first power equals some constant term. So yes, this is a linear equation. Right, this is a linear equation in 3 variables. Right, the x1, x2, x3. Okay, wonderful. And the coefficients, right? I'll write those out as well, since we have a linear equation. The coefficients are just the numbers, the numerical parts of the terms with the variables. Right, the coefficient of x1, the x1 term is positive 5, right? That was that a1 I called it, positive 5. The coefficient of the x2 term is positive 1. Remember, if there's nothing there, I could always technically write times 1, and it's still the same thing. So the a2, right, the coefficient of x2 is positive 1. And then a3, right, the coefficient of x3 is negative 7. Be careful, right? Negatives are part of the terms. Terms are separated by plus signs. So you could technically write this term here as plus negative 7 x3. So negative 7 is the coefficient of the x3 variable. And the constant term, right, the constant term is that b that was being talked about, right? And that's just the term, without a variable attached. Right? And over here it's the number 4. Okay. Right, so I've identified it as linear. It's a linear equation in 3 variables. I've identified the coefficients, the constant term. Wonderful. All right, next example. Same instruction. Say, so determine whether the equation is a linear equation. So I've got 2 variables in this equation, right? There's a variable x and a variable y. This term looks okay. It's got 3 times x to the first. That's what I want in a linear equation, right? Numbers times variables to the first power. So this term has a degree of 1, right? Just a single variable to the first power. But this term, there's a problem. This term has a degree of 2, right? I'll refresh your memory, hopefully. If you've probably seen the word degree before. Remember, the degree of a term in a polynomial, and lots of fancy words, but the degree of a term was the number of variable factors. Number of variable factors. So this has, this term here, this product is negative 4 times x times y. It has 2 variable factors, not 1. So because of this, right, not every term with a variable has a degree of 1. This equation is not a linear equation. So this is not a linear equation. Again, because of that term with the x times y in it. Okay, wonderful. So again, you just have to have a linear combination of variables to the first power. Right, now again, I know x and y are to the first power, but there are two of them, in the same term. You're not going to have two variables or powers higher than one, in the same term in a linear equation. All right, next question, next example. So some fancier numbers showing up here. Pi, which is about 3.14159, right? Pi, that's a real number, times the variable x1 plus the square root of 2. It's another real number, that's about 1.414, times x2. And notice that the x2 is not inside the fancy symbol, right? Is not inside the square root, it's outside of it. Equals 1/3 times variable x3 minus 4 times variable x4 plus the cosine of 3. Right? You trig fans out there, remember that this is not the cosine of a variable. Right? This is the cosine of just 3, just a number. So this is a constant. This is a real number, the cosine of 3 radians. In fact, if I pull my calculator up, we can see that that's approximately, let's pop this up here, just make sure I'm in radian mode. I'm at TI-84 plus here. The cosine of 3 radians, right, is about negative 0.98999, so on. Right? Okay, so this number here is about negative 0.99, but it is a number, a real number. So I'm asking, is this linear? Again, the answer to that question is simply, can I rewrite this in this form, right, as a linear combination of the variables equal to a constant, right, where again all the variables are to the first power. There's only one variable in each term. Let's see. I've already got a couple terms. I'll just take all, let me take all the variables to the left side. So I've already got the number pi times variable x1 plus the number square root of 2 times the variable x2. And then I'm going to subtract the terms with variables and get all the terms with variables on the same side to see if I can put it in that form from the definition of a linear equation. I'd have to subtract 1/3 times x3, so I have negative 1/3 times variable x3. And then, the minus 4x4 is on the right side right now. I would add 4x4, right? So plus 4 times x4 to put it on the left side of the equal sign. Then I have equals, right? That's all the variable terms to one side. And then the term without a variable attached. Now, again, I know there are letters here, but these are not variables. This is the cosine function, cosine of 3 you saw a second ago. This number is about negative 0.99. So you could put negative 0.99 here, and it would mean basically the same thing. But over on the right side, I still have the cosine of 3. So it doesn't matter how weird the numbers look. This is a linear equation. It's a number, a real number times a variable to the first, plus a real number times a variable to the first, plus a real number times a variable to the first, plus a real number times a variable to the first power, equals a real number, right, about negative 0.99. This is a linear equation. And it's a linear equation in 4 variables. x1, x2, x3, and x4. All right, great. Then the coefficients I can easily state. Right, the coefficients, again, I was calling the coefficient of my first variable a1. That's just the number pi, right, approximately 3.14. Right. The coefficient for the second variable, x2, is the square root of 2. Again, I know there's a fancy symbol, but there's no variable in it, right? So it's fine. And that's about 1.414. The third coefficient, right? The coefficient of the third variable x3 is, remember, negative 1/3, or approximately negative 0.33. It's negative 0.3 forever, 33333. And the coefficient of the fourth variable, x4, I'll call a4, is positive 4. Right, and then the constant term, right, the constant term here is this number on the other side with no variable attached. Right, it's just the cosine of 3, and that was that b, right, from the definition, is the cosine of 3, or again, approximately negative 0.99. Alright, so I do have a linear equation, and I can, if it is linear, I should be able to write it in that form where, again, I have a linear combination of the variables to the first power equals some constant. Alright, so how about here? Next one. Right, same instructions. Determine whether the equation is a linear equation. 3 divided by y plus 2 times x minus 1 equals 0. This first term has an issue with it, right? Remember, you could also, remember, you could express 3 divided by y if you wanted as 3 times y to the negative first power. So this is a number, a number times a variable to a power that's not 1. The power on this variable is negative 1. But see, I have a variable in a denominator. Variable in denominator in this first term. And that's an issue, right? I mean, the other two terms look fine, right? It's a number times a variable. Here's the constant term, right? The term without a variable, and here's another one, but I could just add 1 to put it over here. Put all the constants on one side. But again, big problem here. Variable in a denominator. This is not a linear equation. I cannot express this in that form from the definition. So I simply say that, right? This is not a linear equation. All right. Wonderful. All right, and I've got just one more example. Yeah, no, 2 more for this, sorry. So here's another one. Determine whether the equation is linear. Notice the only variable here is x. And look what I have. I have the natural logarithm. Remember, this was that log with a base of e. The natural log of 2 times x equals e to the 5th power. Remember, yeah, there's fancy symbols, but there aren't variables in them. All right, it's the natural log of 2, not the natural log of x or z or something. This is e to the 5th, not e to the x. So sure, I'm seeing the fancy symbols, but there are no variables inside those special symbols. In fact, let me approximate these. I'll show you again the calculator. The natural logarithm, right, that ln of 2, is approximately 0.69. All right, so if I go back here, I'll say this is basically just like this equation. 0.69 times x equals, and then over on the other side, you see I have e to the 5th. E to the 5th is, remember, e is about 2.7, right, 2.718. To the 5th power is approximately 148.441. So looking at this equation, is basically, right, practically looking at this equation, 0.69x equals 148.1. So I do have, see, a number times a variable to the first equals another number, right, a constant term. This is a linear equation, but it's, linear in one variable, right? There's only the variable x. So this is a linear equation, right, in one variable. And that would be, x. Oops. Sorry, going off too far there. Oh, not too far. I just need to get rid of the calculator. All right. Yeah. So it's a linear equation, one variable, x. All right. And then we could state the coefficients, right? There's only one coefficient. That's that natural log of 2, or about 0.69. That's the coefficient of x. And there's only, and the constant term here, that b, right, from the form and the definition, is this e to the fifth, right, about 148.41. Great. All right, so one final example here before we get into the second part of the video on graphing linear equations. So here, is this a linear equation or not? All right, so I have 2 times the sine of variable x1 minus 3 times the variable x2 equals 14. This term's fine. It's got a variable of the first power. No special symbols with variables in it. No variables in denominators. There's a constant term over here. This first term has an issue. You see that special function, right? Special symbol, the sine function, right? It's one of those trigonometric functions. I have a special function, a special symbol with a variable in it. Right, again, I'll put special in quotes here. What do you call special? Special symbol, special function, with a variable in it. That's not going to happen in a linear equation. All right. So this is not a linear equation. All right, and I could go all day long showing you examples and determining if they're linear or not. But again, just can you write it in this form? Right? Can you write the equation in this form? If you are able to, get a linear combination of these n variables, however many variables there are, equal to a constant. If you can express it this way, and there's every variable's to the first power, so there's nothing squared, nothing cubed, no special symbols, no special functions with variables in them, and also no variables in denominators, which would imply again that you have powers other than one on those variables. If you're seeing all that, great, it's a linear equation. If any of these are violated, then it's not a linear equation. All right. So that was it for the first part of this video on just identifying whether an equation in so many variables is linear or not. Now I'd like to talk about graphing linear equations for the latter part of this video. All right. So a graph is simply a picture of solutions. You've most likely, if you're throughout your mathematical careers, have most likely heard the word graph before and solution. But just to recap here. All right. So a solution of a linear equation, and again, here's the general form here of a linear equation, the way I had it earlier: a1x1 plus a2x2 plus plus anxn equals b. A solution of an equation like this is a list, an ordered list of n elements, one for each variable. Right? If it's got n variables, a solution is an ordered list of n elements called an n-tuple, or n-tuple. I've heard both pronounced. I'm going to say n-tuple. Right. Written as, you got some parentheses with, a value for the first variable, comma, a value for the second variable, comma, a value for the third variable, etc., dot, 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 comma, and a value to replace the last variable with that satisfies the equation. That actually, when I plug these values in, when I plug in the value here for x1, the second value for x2, the third value for x3, and so on, I get an equation that is a true statement, right? The value on the left side is equal to the value on the right side. That's a solution of an equation. All right, and then a graph. Right, when you're asked to graph anything, it's just drawing a picture to represent the solutions of that equation. So a graph of an equation is a picture or a pictorial representation, if you want to say it in a fancy way. It's just a picture of its solutions. Okay. All right. So we're going to start with equations with a single variable and work our way up. So graphs of linear equations in one variable are just a point, just points on a real number line. Now you're going to see this symbol, or if you haven't already, but you're going to see this quite a bit in my videos and many other people's as well. This big R with a double bar here, fancy script R. Well, not really a script R, but a fancy R. This is the set of real numbers. Right, so usually represented by a real number line. Okay, the set of real numbers. So for example, here's a linear equation in one variable, right, just x. So let's graph 2 times x equals 6. Now because there's just, it's a linear equation in a single variable, my graph is going to be one-dimensional, meaning I'm going to graph it on a single number line, which I have down here. So this number line, I'll call, because the variable is x here, I'll call this the x number line, the x-axis, or a number line representing possible values of x. Well, when you have a single variable, right, a linear equation with a single variable was very easy to solve. You probably have seen this, right? I would just simply divide by 2, and our solution, right, the solution to this equation is a 1-tuple, which would be the number 3. Right. The number 3, right? The solution is x equals 3, right? If I replace x with 3, 2 times 3 is 6. There you go. Right? You get 6 equals 6. It makes it true. Now, a 1-tuple is silly. All right? You don't have to say 1-tuple. A 1-tuple is just a real number. All right, so usually the parentheses aren't needed, right? You just write without parentheses. Write without parentheses. Because there's nothing coming after it, nothing coming before it. So really there's no need for parentheses around a single number. Alright, and then I want to graph this, right? Draw a picture. Well, there's a single variable, right? Single number line representing possible values of that variable. And yeah, where's the number 3 represented on this number line? So again, remember 0 in the middle, positive 1, 2, 3, 4 to the left, to the right, negative 1, negative 2, negative 3, negative 4 to the left, and so on. There it is right here. There's a point. All right, there's the number 3 drawn on the number line, right? So again, just a point on the number line. is the graph of a linear equation in a single variable. And that's it. That is the entire graph, the picture of all the solutions, like the only solution to this equation. All right, so this was one equation with one variable, had just the one solution. Now we're going to bump it up a bit. All right, and I'm going to go to 2 dimensions, right? Two number lines, 2 variables. And you're going to see that when there are more variables than equations, you're going to have infinitely many solutions, right? So that's what we got here. Next, we're bumping it up a dimension. Right? So graphs of linear equations in 2 variables are lines, not just single points like the last one, in 2-dimensional space. Now we're going to talk, if you're in a linear algebra class, you're going to talk a lot more about space and dimension. Those concepts will be fleshed out a little more in later videos of mine. Right. Now, 2-dimensional space, when you have 2 variables and the solutions are 2 tuples or ordered pairs, which we'll see in a second, that space where you're going to graph your solutions is usually represented by R2. Right? It looks like R squared. Remember, this was the symbol for the real numbers, and this basically tells me I'm looking at a space where there are 2 number lines, or we're looking at equations with 2 variables. All right, so R2. It's said like this. I just say R2. Right, R2. But it's filled with ordered pairs where each number is a real number. All right, so for instance, here is a linear equation in 2 variables, x1 and x2. Now, as I mentioned earlier, when there are more variables than there are equations, right, there are 2 variables, only 1 equation. Some of the variables will be called free variables, meaning you can let them be whatever number you wish. And you're going to have infinitely many solutions. All right, so I'll say it one more time. If there are more variables than equations, you're going to have infinitely many solutions. All right, so let me write up some examples of solutions here. So some solutions, put it here, to this equation. Now remember, these are going to be 2 tuples. Right? We have 2 variables. Now another word for 2 tuples would be ordered pairs. Right? Ordered pairs. And they're going to be pairs of numbers like this, where the first value is, say, the value of x1, then a comma, and then the second value is a value of x2, and then parentheses around them. And they're going to be pairs of numbers like this, such that when I replace x1 with the value in the first slot and x2 with the value in the second slot, I'm getting a true statement. So here are just a couple. Now to find solutions, right? You just pick a value for when there are 2 variables and only 1 equation. Remember, it was easy to solve when there was 1 equation. It was easy to solve when there was 1 variable. So you pick a value for one of them, whatever you want. Say x. So I would consider x2 a free variable, and that notion of free variable would be discussed much more in later videos. I pick whatever I want for x2, and then once I do, I'll have an equation with 1 variable, x1. For instance, if I were to pick, here I'm making an ordered pair here. If I were to pick, x2 to be 0, I replace x2 with 0. Can you see when I do that, it gives me an equation with 1 variable, one equation with 1 variable, and that's easy to solve. Now 4 times 0 would be nothing, that'd be gone, and then I'd have 3 times x1 equals 12, divide by 3, x1 would be 4. So 4 for x1, 0 for x2. There's one solution. Now how is that represented? Well, two variables, going to have these two perpendicular number lines, one for each variable. Alright, so let's say this horizontal number line represents the values of x1, and the vertical number line represents the values of x2. Now they're both real number lines, right? So you got, for the horizontal one, I have a 0 in the middle, and I'm going to have every notch, every square here represent 1 unit. So there's 1, 2, 3, 4, etc. on the first, and then going the other way, -1, -2, -3, etc. And then the vertical number line, still a number line, so you have 0 in the middle, and then it goes positive up, 1, 2, 3, 4, and so on, and then negative down, -1, -2, -3, and so on. So where is this solution? 4, 0. I go to where is 4 on the x1 axis, where is 0 on the x2 axis, and then I plot the point that's in line with both of those. And that would be this point here. All right, there's the ordered pair 4, 0. Right? It's 4 on the x1 axis, and then it's in line with 0 on the x2 axis. But that's not the only solution. As I said earlier, when there are more variables than equations, you're going to have infinitely many solutions. Because I didn't have to choose 0 for x2. I could have chosen anything I wanted for x2. So another solution. Say I chose 3. Or how about -3? That would make it easier. How about -3 for x2? If I replace x2 with -3, this equation would now become 3x1 plus 12 equals 12. Then I would subtract 12, get 3 times x1 equals 0, divide by 3. x1 would have to be 0. And you can, again, double check this. Replace x1 with 0. Replace x2 with -3. You're going to get 0 plus 12 equals 12. You'll get 12 equals 12. That is a solution. All right, so then I plot this one. 0 on the x1 axis, so I'm in the middle here, and then -3 on the x2 axis, so down 3. This point, right, corresponds to both of those. There's 0 on the x1 axis, and then -3 on the x2. That's the only point that's in line with both of these numbers. All right, I mentioned to you that the graphs of these are going to be lines, right, in R2, lines in two-dimensional space. And to graph a line, you only need 2 points. But you could find other solutions. I could find lots of other solutions. So I'll just find one more. Right, I'll just find one more. Okay. So how about I'll replace x2. I'll replace x2 with 3. Positive 3 this time, instead of -3. That'll make this -12. I'll have 3x1 minus 12 equals 12. Then I would add 12 to make 24. 3x1 equals 24. Then divide by 3. x1 equals 8. I get x1 is 8. x2 is 3. And I'll plot that, right? So here's 1, 2, 3, 4, 5, 6, 7, 8 on x1. And then positive 3 on x2. So we're at this point here. This is the only point that's in line with both of those. There's the ordered pair 8, 3. It's in line with 8 on x1 axis and 3 on the x2 axis. And again, if you do enough of these, you'll see that they do indeed, all these solutions to this equation will indeed form a nice straight line in R2 here in two-dimensional space, which I'll draw here. Just draw on the rest of them, because again, there are going to be infinitely many. I can't do this all day. Right. So there's a graph, a picture of all the solutions, going in both either direction forever. And just to show you a little better picture, I'll go to a recommended website for you. This is called desmos.com. It's a free online graphing calculator. And here I've just entered the equation. Now I know the equation looked like this. Right? It was 3x1 minus 4x2. But again, I said earlier, you don't have to call these x1 and x2. You can call this x and this y. And then the horizontal axis would be the x-axis. The vertical number line would be the y-axis. So that's what I've done here just to make it simpler. So you see I have the same equation, 3x minus 4y equals 12 drawn in, and there it is, right? And you see there's that point 4 comma 0 that I mentioned earlier. That's one solution. 4 for x, 0 for y. There's 0 comma negative 3. That was another solution on my page. But notice how it has infinitely many more. I mean, look at all these points here. 5.23, 0.923 is a solution. 1.9, negative 1.575 is another solution. Negative 1.5 for x1 and negative 4.125 for x2. There's another solution, right? I can go all around here and find and look at all sorts of different solutions to this two-variable linear equation. But you see that picture though? It looks exactly the same as the picture I have here. Right? This line going up to the right. Right. Great. So again, hopefully this was familiar, right? You probably had this in some algebra class before. Right. All right. So graphs in one dimension is just a single. Graphs of linear equations in one dimension is just a single point. Graphs of linear equations in two dimensions is going to be a line. Graphs of a linear equation in three dimensions is going to be a plane. All right, so not an airplane or anything like that, but a plane is just like a sheet. It's like a sheet of paper, right? It's a sheet of paper, but extended off in both directions, infinitely in all directions, right? It's just like a large sheet, infinite sheet of paper, a flat plane. So graphs of linear equations in three variables are planes in three-dimensional space. And again, three-dimensional space will usually be represented in like a linear algebra text as R3. Right. So this just tells me I have three real number lines that all intersect at 90-degree angles. Right. Just like R2 was two real number lines intersecting at a 90-degree angle. All right. This is representing three real number lines intersecting at 90 degrees. Now, I am drawing here on a sheet of paper. My sheet of paper is a two-dimensional space. There's only left, right, and up, down. So I can't draw on a sheet of paper. I can't draw a three-dimensional space. I can only represent it as best as I can. So I have these three axes. All right. Three axes, three number lines, because this is an equation with a linear equation in three variables. I have x1 plus 2x2 plus 3x3 equals 6. Or you could go x plus 2y plus 3z equals 6. Still a linear equation in three variables. Now I know, again, it's on a sheet of paper, so it doesn't look like these aren't meeting at 90-degree angles. I mean, these two are. Right? You can see the 90-degree angle there. But we have to imagine, because it's the penalty when you lose a dimension. Right? We have to imagine that this third line I drew also meets these axes at 90-degree angles. All right, we have to imagine that it's coming out of the page straight toward you. All right. So I'm going to call this axis that we're imagining is coming straight out of the page, right, straight toward the camera. I'll say this. Let's say this is the x1 axis, and then this axis that's horizontal here, that's perpendicular to this. Again, I know it doesn't look perpendicular, but you have to imagine that. I'll say this is the x2 axis or the y-axis. So the x-axis, y-axis. And then the one going straight up and down, that is, again, perpendicular to both of these other two, even though it doesn't look it, you have to imagine it, is the x3 axis. All right, and they're all number lines. They're all real number lines. So I got 0 in the middle. And then going on the one x, let's say coming toward us, coming out of the page, we got 1 unit, 2 units, 3 units, 4 units, etc. And going behind the page, going back, say that's -1 unit, -2, -3, -4, etc. All right, and then the x2 axis is also a real number line. Where 0 in the middle, and let's say going this way is the positive direction, so 1, 2, 3, 4, and so on. And say going this way is the negative direction, -1, -2, -3, and so on. And then the x3 axis is another real number line. Let's determine that going up is positive direction, 1, 2, 3, and so on. And going down is in the negative direction, -1, -2, right? So -3 and whatnot. All right, so lots of things to keep track of here. All right, so this time, the solutions, right? The solutions of this equation is going to be a 3-tuple. The solutions of this equation are going to be 3 tuples. Another way to say that would be an ordered triple. Right, you had ordered pairs for two-dimensional space, ordered pairs for R2. Now we're in R3. Our solutions are ordered triples. Right. And every single one of them is going to look like this. You'll have, in parentheses, you'll have some value for x1, the first variable, comma, some value to replace x2, comma, some value to replace x3, comma, and then each one, and I want these so that they make this a true statement, right? That we get 6 equals 6. All right, so I'm going to put in just now, remember for a two-dimensional line, you only need 2 points. For a plane, to draw a plane, define a plane, you need 3 non-collinear points. You need 3 points that aren't on the same line. All right, so I'm going to find 3 solutions here, and then again I'll go to another website and show you a better picture than the one I draw. All right, so here are some solutions. So some examples of solutions. Again, there are more variables than there are equations, right? There are 3 variables, 1 equation. So there's only 1 equation and 3 variables, so there are going to be 2 free variables. I could pick x2 to be anything I wanted, and x3 to be anything I wanted, and then once I do that, then I can solve for x1. Right? I'll have 1 equation with 1 variable. In fact, that's going to be kind of the formula. The number of variables minus the number of equations will typically be the number of free variables. Again, the concept of free variable will be better established in another video, not this one. All right, so here are some examples of ordered triples or 3 tuples that are solutions to this equation. 6, 0, 0 is an obvious one. 6 for x1, and then 0 for x2 and x3. 6, 0, 0. All right, so where is that point? So that's 6 on the x1 axis. So that, remember, I was coming out of the page. So there's 4, 5, 6, 6 on the x1 axis, and then I'm not moving in the x2 direction or in the x3 direction. So this is on the x1 axis here. So there's the point, 6, 0, 0 that I just labeled right here. Okay, another one, again, I'm just picking some easy solutions. If x1 and x3 were 0, then x2 would have to be 3, right? You get 2 times 3 equals 6. So 0 for x1, 3 for x2, 0 for x3. All right, would make this 6 equals 6, would make this true. All right, so where is this? So 0 in the x1 direction, no, not moving. 3 in the x2 direction, a positive 3 was this way, and then 0 in the x3 direction. So we're on the x2 axis. That's that point right there. Again, I'll label it 0, 3, 0. All right. Then finally, another solution on the x3 axis would be 0 for x1, 0 for x2, and 2 for x3, right? 3 times 2 is 6. So 0 for x1, 0 for x2, and 2 for x3. And again, there are infinitely many. These are not all 3. There's many, many more. I can just pick any value I want for 2 of these variables and solve for the third one. All right, so where is 0, 0, 2? That's 0 in the x1 direction, 0 in the x2 direction, then 2 up in the x3 direction. That's this point here. All right, so there's the point 0, 0, 2. All right, so I have 3 points that aren't on the same line. All right, and what they're gonna form is a plane. All right, a plane, a sheet. I mentioned the graphs of linear equations in 3 dimensions are a plane. All right, so how am I going to form that plane? All right, I'm going to show you. I'm just going to show you part of the plane. I can't show you the whole thing because a plane goes on forever in 2 directions. Right? So I'm going to connect these points. Right, this was 6, 0, 0, and 0, 3, 0. I'll draw a little segment connecting these two, maybe with a better marker. Okay. And then I'm going to do the short one. Connect one of these other pairs of points, and we'll get the 2 directions. Right, a line is defined by 1 direction. A plane is kind of defined by 2 directions, spanned by 2 lines. You'll see the concept of spanning vectors and all that in later videos. Right, and then to kind of represent this plane, I'm going to try to represent it in the same fashion I did here, where like I'll draw a segment parallel to this over here. I'm going to make a little like parallelogram. Right, I'm going to do a little parallelogram to represent a sheet, a plane in this R3, in this 3-dimensional space. So this was what, 3 left, 2 up. So I'll do the same thing over here. I'll go 1, 2, 3, 2 up, and then kind of this point here. Let's say this represents another solution. So I mean, if I did that, that would be what? Okay, and then I'll just draw this parallelogram here. Right. So this segment is kind of running in the same direction as this segment. Right. Let's draw this parallelogram. And then this direction between these two is running in the same as this direction here. And then I'll do a little shading, like we get a plane, and this is not all of it. Right? This is like just it's a sheet of paper that goes on forever, and backwards and forwards and forwards, up, down that way, out that way. Right? It's a sheet that goes on forever. But it is a sheet, a plane. So here's a representation of this plane in R3. And every single point on this blue sheet that I just drew represents a solution of this equation. All right, so let's take a look at a better picture of this. All right, so I got now a website that's good for drawing 3D graphs is geogebra.org, geogebra.org, and they have a 3D calculator that you can find. So here it is. Now, their orientation's a little different than mine. I'll turn it to kind of be like mine, but their red axis is like the x-axis, their green axis is the y-axis, and the blue axis is the z-axis. So it's like the red is like x1, the green is for x2, the blue is for x3. So remember my equation was x1 plus 2x2 plus 3x3 equals 6. I just replace that with x plus 2y plus 3z equals 6. Right. And we see a plane. See, it's a sheet, and I can rotate this so it looks more like my drawing. See where x1 is kind of coming out at you, and x2 is going this way, and x3 is going up. But I get this plane, a sheet of solutions. And here's the solution 0, 0, 2, right? That is on, see that blue axis, the z, you can see it's on the sheet. Right, you can see it's on that sheet. When I rotate this a bit, then here's 0, 3, 0, right? 0, 3, 0. Again, this is on the sheet, right? Definitely on that piece of paper, on that plane. And then here was 6, 0, 0, another one I graphed for you. And again, you can see that that red point that just showed up is on the sheet, on the plane of all the solutions. And we can find other solutions, right? Oh, actually, that was a bad idea. All right. We can find other solutions again by plotting, just picking, like I said earlier, pick a value for 2 of the variables and solve for the third one. So like another solution, which I'll plot here, say a point called point D. If I said let's have x1 and let's have y and z be 1, 1, 1, 1, right? If x was 1 and y was 1 and z was 1, you'd get 1 plus 2 plus 3 equals 6. So 1, 1, 1. There's a point. And you see that point that just popped up here, this blue point 1, 1, 1, that's definitely on the sheet. You can see it here. It's on that sheet. Right? So yeah, and then again, you can plug in fractions, plug in any real numbers you want for 2 of the variables and solve for the third one. And we get infinitely many solutions, a whole plane of solutions in 3 dimensions. Right? So hopefully that picture made it a little nicer to look at than what I have here. Right? Mine's not terrible. It's just, you can't, it's hard to envision, right? It's hard to go up from, it's hard to envision a 3-dimensional thing on a 2-dimensional piece of paper. Right? And then after that, a linear equation in 4 variables, a linear equation in 5 variables, and so on. You can't picture those. We only live in 3 dimensions. I cannot draw a picture. I can try. I can throw in another axis maybe and just imagine stuff, but like even imagining 4 dimensions and 5 dimensions is difficult, if not impossible. But if I have an equation in 4 variables, right, the solutions will be 4 tuples, and then 5 tuples for equations with 5 variables, 6 tuples, 7 tuples, etc. Right? For 2 tuples and 3 tuples, usually they're called just ordered pairs and ordered triples. But after that, calling them 4 tuples, 5 tuples, 6 tuples is usually the convention. N tuples. All right, so I hope this was good, a good introduction to linear equations and their graphs. And I hope the examples made sense, how I plotted the solutions and drew a picture with a few solutions on there for lines and planes and points. And just I hope you enjoy practicing problems like this where you're asked to determine if an equation is linear or not, and also graph a linear equation, or at least look at a graph of a linear equation. And one other thing to say too is if you're looking at a graph, if you're looking at a graph in 2 dimensions with 2 number lines and the graph isn't a line, then the equation can't be linear. If you're looking at a graph of something in 3 dimensions with 3 number lines and the graph isn't a plane, then the equation wasn't linear, right? Linear equations have to have graphs that are lines in 2 dimensions, planes in 3 dimensions, just a single point in 1 dimension, right? Going back to the 1-dimensional, it's just a single point in 1 dimension. But if it's not one of those things, then it's the equation wasn't linear to begin with. All right. So I hope you enjoyed this. Hope it made sense, and thank you very much for watching.